Problem number 5. Temperature at which water boils depends on the elevation. A higher elevation, the lower the boiling point. At sea level, water boils at 2012 degrees Fahrenheit. Elevation of 10,000 meters, the water boils at about 155 degrees Fahrenheit. So here are the boiling points listed below. Let's see. Part A, let B be the boiling point in degrees of Fahrenheit. So we'll call this B. And E, 1,000 meters. So let's call this E. Create a scattergram for the data and draw a line that comes close to the point in the scattergram. Alright, so first let's create a scattergram, and we'll do this using our just doing this by hand and estimating. We got 1, and then this is immediately going to go to 5, so we have to use our line here a little bit wisely. We're going to go to 15, so I'm going to jump to 5, 10, and 15. And then our boiling point here goes all the way up to 212 and starts at 175 or 127. And it's hard to kind of set this up evenly, but let's see what we can do. Maybe I can just put tick marks here to identify from 127 to 200. There's a lot more space there because there's about 73 steps over here, and this is just 15, so I have to make space here. 182 and 155 and then 127. So let's just say it looks something like this. And it's really best to do this on your graphing calculator, but we're going to try to do this without a graphing calculator for now, just to get some ideas. So our E values, by the way, this is our boiling point temperature, and this axis is going to be your elevation axis. And then we're going to plot points. We need 0. I'll plot points in a different color here so that we can see. 0, we have the boiling point at sea level. We have the boiling point at 212. Now we have 1 and 2. 1 and 2,000. 1 and 2,000 would be over here. So this is 205 and 200. At 5, this is going to spread out a little bit now, a little bit further now. It's 182. At 10, it's 155. And at 15, it's 127. Okay, so it doesn't fall exactly in a straight line, which is okay. But they do ask us to draw a line that comes close to the points in the scattergram. Okay, so this is just a little bit of eyeballing and estimating. So it has to probably be below 212, and so my line would probably go something like this. It doesn't pass through all the points. It probably, like I said, the way this is set up, it's not going to pass through every single point. But I know that it's decreasing. It has a little bit of the points have a little bit of a curve, and so the line just has to go through it as best as it can to get close to all the points, not just 1 or 2 points. Okay, let's see if we can answer the next question. The height of a certain mountain is 800 or 8,800 meters at its peak. What is the boiling point of the water at its peak? So 800. So this is in thousands. In thousands of meters. And this is your degrees Fahrenheit. So if we look at 8,800, that's past 5 and close to 10, close to 9 actually. So let's see if we can let's call it 8.8, and then this is going to be a value. It looks like it's between the 5 and 10 value, so 8.8 would go probably somewhere between here, and at this point it's a matter of guessing. So let's guess to be about 160 or 170. So again, that's just a guess, but we can guess that. So at 8,850 meters, boiling point is about 170 degrees Fahrenheit. And, you know, this is an approximation. Next question is that did this require interpolation or extrapolation? So, since this is within the data set that we have, this is going to be interpolation. So interpolation is to make your guess within the data set, and extrapolation is to make your guess outside of the data set. So this is interpolation because 8,850 meters is within the given data set. Next one, we say water is lukewarm if its temperature is close to the body temperature of 98.6. What is the elevation of at what elevation would boiling water feel lukewarm? So now, this time, we are looking at a value. We see that the boiling point here kind of goes down, it's decreasing. So at 98.6, we would probably guess 98.6 would be over here, and it would give us thousands of meters. Now this is going down, kind of started to go down slowly, and by making jumps of 5 here from 10 to 15, we went down, let's see, 155 minus 127, so we went down about 48. So we can probably guess that another step of 5 over here, when this is 20, we can get down another 48, maybe a little bit less than that. But if we get 127 minus 48, this is subtraction. Let's see, we get 79. So that's probably low, but remember that it's decreasing, so we know that it's going to go down. We could have guessed maybe 18 instead of going all the way up to 20, but let's just stick with 20. So it'll be at about 20,000 meters above. So we can say at about 20,000 meters boiling point is about 98.6. Now the next question, is it interpolation or extrapolation? This is clearly way out of the bounds of our data, so this is extrapolation. And our reason would be outside of data set. Okay. All right. Now let's take a look at this last question. See if we can move this question over here a little bit. The cooking time required to make hard-boiled eggs depends on the water temperature. So let T be the amount of time in minutes it takes to cook an egg in boiling water at an elevation of 8,000. So sketch a qualitative graph between E and T. So this is E and B. We want E and T. And let's see if we can translate this. Let me redo this table where you have E and B. And you got 0 to 12, 1, 205, 2, 200, 5, 182, 10, 155, and 15 and 127. So let's extend this graph or this chart to include the cooking times. So at boiling, you're cooking an egg and the water is at 212. So this is going to take, let's say it'll take about 10 to 12 minutes. Now your water is boiling at 1,000 meters up. Your water is boiling at 205 degrees Fahrenheit. Well, if it's cooking at 200 degrees Fahrenheit, the egg is going to take longer to cook because you're not as hot as 212. Your water is boiling, you put the egg in, and it's going to take longer to cook. So let's just say this will take another 3 or 4 minutes. And you go further up, it's still going to be kind of your temperature goes down. So now when you put the egg with a temperature of 200 degrees, it's going to take longer to cook, even longer so. So it looks like our graph is going to be increasing. And then now there's a bigger dip between 200 and 182. So it looks like this would take even longer than just another 3 minutes like we've been doing here. So this might take maybe another 9 to 10 minutes. So we can see that. Let's start thinking about how our graph is going to go. You can see that this is your E, your elevation, and now this is not your B, but this is your T. What we have here is a relationship that starts at a specific point here, 12. Now I want to not look at this. I just want to concentrate on the relationship between E and T. And I have 0 at 12, 1 at 15, 2 at 18, and so it looks like our graph is going to be increasing. Okay? So I don't think they're going to have labels on this. This is going to end up being a multiple choice. But the point is that because the water boiling is going to be uh, less hot. It's going to take longer for the egg to cook. So higher elevations, longer cooking time. Okay, so yeah, this last question is a tough one, but it does take some information about um, the water boiling and the relationship in the water boiling and the amount of time that an egg will cook. And so just think about that if your water is not that hot, then your egg is going to take a longer time to cook. So this last one is probably going to take, you know, probably could take 45 minutes to cook. All right, so good luck with this problem.